Hello everyone, I hope you are doing well. So in today's video, we are going to go through the 2024 VCE sample chemistry exam, part 1 of the short answer questions. And like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. Again guys, just a disclaimer, these are my suggested solutions. If you guys see any mistakes, silly mistakes, please let me know. I will have a look at them. Now, I'm making these solutions because basically VCAR doesn't post the answers for the sample. It is just a sample, so most of the time your teachers will make their own solutions and give it to their students. But if you guys are struggling to understand some of the concepts, I hope this video finds you well and helps you with your VCE chemistry studies, especially it's a new study design. So yeah, let's smash through this video. Question 1. In a school laboratory, Amelia and Dylan fermented plant biomass and then distilled it to produce bioethanol. State which one of the 7 principles of green chemistry is the most relevant to the production of bioethanol from fermentation. Use item 26 of the data book. Easy. So in the new data book, there's actually they've basically listed the 7 principles of green chemistry, and it's at the end of the data book. So if we go down here, right here, green chemistry principle, and there's 7. Now, we need to look at which of these principles is talking about the principle of the production of bioethanol from fermentation. And you straight away realize, wait, if you're making ethanol from fermentation, it's renewable. It's a renewable fuel. Like you're making bioethanol from fermentation. You're not actually using, you're not creating it from coal where now it's, a fossil fuel. So yeah, absolutely. So it's not, atom economy. So it's not this one. It's not catalysis. It's not designed for degradation, designed for energy efficiency, designed for safer chemicals, prevention of waste. It's this one. The last one right over here is the perfect thing that really is why we create bioethanol from the fermentation. We're trying to use renewable feedstocks. That is, basically, this is the best definition. Raw materials or feedstock should be made from renewable, mainly plant-based. And that's true. Normally, we ferment sugar, not ferment, but sugar cane or stuff. We basically ferment them and we basically break them down to, so we get its glucose and we ferment that glucose into ethanol. That's our bioethanol in this case. So materials rather than fossil fuels wherever practical. That's pretty much what we're doing. We're not using coal. We're trying to use, we're fermenting basically plant biomass to create bioethanol. So the best in this case, because it says, is the most relevant to the production of bioethanol is the use of renewable feedstocks. So put that there. So use of renewable feedstocks. Let's write that down here. Okay, so let me write it. What? I want to see the size. Normally it's 4. Yep. Use of renewable feedstocks. That is the first one. Perfect. I don't know why it's so... I want to make it like 3 maybe. Yep. The following equation represents the production of bioethanol from glucose. Beautiful. This is the fermentation reaction. So this one. Please make sure to memorize this. This comes up in most of the exams, and they're like, write down the fermentation of glucose. What does it look like? And so it's this here. We ferment glucose and we produce two basically bioethanols and a CO2 molecules. And we're basically given also the molar masses for all of the molecules. Calculate the percentage of atom economy for the production of bioethanol from glucose. Easy. So looking at your data book, there is the formula for percentage of atom economy. It's, I think, in the first following pages. Here it is. So atom economy right over here is what? It is the molar mass of the desired product divided by the molar mass of all the reactants. So what is our desired product? It's actually your bioethanol, your ethanol. And what is the mass of all reactants? It's this. It's your glucose. There's only one reactant. It is glucose. So, and we want them. It's basically all the molar masses. So let's do it. So what is the molar mass of ethanol in this case? What's the molar mass of ethanol? They've given it already to us. It's 46. But remember, there's 2 of them. So we're going to write 2 times 46. Because that's, remember, so this, basically an ethanol has overall 46 molar mass, but there is 2 of them, so double that. Divided by the molar mass of your reactant, which is just basically 1 glucose molecule, which is 180. So let's write 180. and multiply by 100 to make it a percentage. And we get, what? It's 4 times, 2 times 46 divided by 180 times 100. And we get, to how many significant figures? 3, it looks like it. 51.1 percent, not grams, percent. Done. That's that one. Easy, that's your solution. So calculate the percentage yield of ethanol if 100 grams of glucose reacts to form 7.15 grams of ethanol. Easy. So let's look at our yield. What is our percentage yield? How do we calculate it? It's also in your data book. Percentage yield is the actual yield divided by the theoretical yield, and we times it by 100 to get a percentage. Now, yield is measured in grams. Remember, it's mass. So it's the actual yield. So think of it like this. So basically, when you're reacting, 100 grams of glucose, you will you only form 7.15 grams of ethanol. This is what we call the actual yield. Now, the theoretical yield is where you basically do calculations with it, because you assume that there's 100% efficiency. So you would use your you would use your mole ratios. Like, for example, you'll convert this into mole and then convert get the mole of mole ratios to get the mole of ethanol, and then convert that to grams, and that's going to be like if it was 100% efficiency. So that is what we call the theoretical yield, and that's what we basically need to calculate. So we already have the actual yield, which is 7.15, but we need to calculate that theoretical yield. So what we need to do first is actually to find the mole of glucose. Now I can't be bothered writing glucose, so I'm just going to write glu. Is, remember, it's mass over molar mass. The mass of glucose we're using is 100 divided by, what's the molar mass of glucose? It's 180. That's going to result me in basically 0.55 mole of glucose. And then we're going to use, of course, more ratios. Now, we can see it's a 2-to-1 ratio to get ethanol mole. So to get the mole of ethanol, which is C2H 5OH, it's going to be 2 times the amount of your glucose, the mole of glucose. So that's going to be times it by 2. You get 1.11 mole. And now what we need to do is convert it into mass. Now remember, the mass, all we have to do is basically multiply the mole by the molar mass. So 1.11, we multiply that by the molar mass of ethanol, which is 46. And that gives me 51.1 grams. Done. So this here is your theoretical yield if it was 100% efficiency. So now we've got those. Remember, now putting it into the yield formula, it is your actual yield, so 7.15, divided by your theoretical, which is 51.1, and you multiply by 100 to get it into terms of percentage. So overall, your percentage yield is going to be equal to, it's going to be 7.15 divided by that times by 100. It's basically, to how many significant figures? It looks like 3 is the lowest, so it will basically be 14.0%. The right percent. I was going to write grams, but yeah, it's a percentage yield, so looks like that's your answer for that one. Now, luckily, there's nothing new in this. It's still in the old study design, all these questions, so that's good. C. Explain why fermented biomass require distillation by Amelia Andelin to produce usable bioethanol. Now, this isn't in the new study design. You should realize that this is the problem. When we're, why do we have to distill it? Why do we distill, bioethanol when we ferment it? This is why. So basically, when we're fermenting it, what we get is basically this bioethanol. Now, what do you see that is problematic with it? It's that it's in its aqueous state. It means it has water in it. And remember, what happens if you have a fuel with water? Its efficiency is destroyed. It's useless. Now, normally, normally when you look at the textbooks, it's approximately when you look at it, it's only like 10% actual pure, right now, like when you just basically ferment it, you only get like around 10% pure ethanol. So it means that in the other 90% is water. So it's actually mostly water. It's a useless, fuel. It's not very usable. So what do we have to do? What do we basically, it's a volume to volume, by the way. So 10% volume to volume. So how can we, make sure to have the most purest or the high concentration of that bioethanol? Because remember, we need to get a high concentration of bioethanol, meaning that then it can be used as a fuel. How do we do that? Well, the only way is to get rid of that water. And how do we get rid of it? We use distillation. And basically distillation is you like take the boiling point. It's all about the boiling points of ethanol. So ethanol and the water. So bioethanol, we said it's a mix. It's a mix of water and actually pure ethanol. Now, if you don't realize, ethanol has, I can't get it in my head, but it's, I think, around that 70 degrees Celsius, basically its boiling point, whereas water is, of course, 100 degrees Celsius. Now, what we do is when we use a distillation, it's in the new study design, what we do is we make sure it's between that range. Let's say we use 85 degrees Celsius. What's that going to do is basically ethanol, because it has a lower boiling point, it's going to become gaseous. It's going to become gaseous and it's going to go up the chamber. And so, of course, water, it's very, its boiling point's 100. It's still liquid. It's at the bottom of the chamber. So that pure ethanol is going to go up, and that's what we take. That's what we take, and that's the pure ethanol. And so, absolutely, that's what we have to distill it, because when we distill it, we make pure ethanol. And so that is what we can use. That becomes useful for cars, and that's what we need to use. So I hope that makes sense. This is in a new study design. Remember, I can guarantee that it could be in your exam. Basically, VCA always tries to put the newer stuff to try to make an example of the first year students, especially like you guys. So remember, you need to know about it. Distillation is very important for ethanol. So bioethanol, you need to distill it, because it's in its aqueous state. It has water. It's very useless. So let's write down what we said. All right, so we're going to say fermentation. I'm going to try to write a lot, try to go in deep detail, so a lot of students, when they read it, can understand what I mean. So fermentation produces ethanol in its aqueous state. Who cares if you spell it wrong? Aqueous state. Meaning it has water. So it has water and has a low concentration. So low concentration of bioethanol. Now, approximately, it's known to be 10% volume to volume. I'll make sure to memorize that. So most of the books that you'll read, like the Heinemann, Jacaranda, they say around that 10% to volume. So for bioethanol to be useful. So for bioethanol to be useful, a higher concentration. So a high concentration is required. So water must be taken out. Through the process. Through the process of distillation. For it to become pure bioethanol. Beautiful. Now, of course, I'm not going to talk about distillation. It's just tell me, for 2 marks, it's just tell me why do we distill it? It's because it's mostly water. You need to make sure to distill it to make sure it's pure bioethanol. So yeah, I hope that makes sense. That answer makes sense for you. And yeah, that looks good. So let's try a question 2 now. So The following thermochemical equation shows the complete combustion of methane under standard laboratory conditions. So we've got this, and we can see the enthalpy change. The activation energy for this reaction is 230 kilojoules. Complete the following energy profile diagram for the complete combustion of methane gas. Indicate on the diagram the change in half, so the enthalpy change and the activation energy. Easy. So they've already drawn us this. So I'm going to just say this is 0. Start off 0. And so we're going to look at the activation energy first. So it rises up to 230. Now, I'm going to make sure, like, I'm going to make these all 100. So 100, 200, 300. So it will be around, so it will rise up to 230. That's, so that's 1, 2. So it's around, like, here. It's like halfway, like 230. So I'm just going to, what I'm going to do is, I'm going to draw this, like a straight line. And I'm going to draw it like this, rising up to that. Oop, it's not the most looking nice like that. Yeah, it's not going to do it. So I'm going to just have to nicely do it like that. Okay, perfect. That's like the maximum reach. And then it will go down. And remember, the enthalpy change is the difference between the energies of the product minus the energy of the reactants. So we know that enthalpy change is negative 890. So it's approximately like negative 900. So that's 100, negative 100, 2, 3, 4, 5, 6, 7, 8, 9. So approximately it will be around here. I'm just going to draw this line for reference. Let me just draw these out. Okay, so it's going to come down like this. It's going to come down and then here and become horizontal. I'm just going to rub these out now. That's what it will look like basically, yeah. Nice. And we just have to now label the enthalpy change and the activation energy. So remember, the enthalpy change, so the activation energy is from the reactants to the maximum peak. It's right here. That is your activation energy. And remember, your change in enthalpy is the energies of the reactant, like the products minus your reactant. So it's this here. And that's your enthalpy change. Easy. Nice 2 marker. B. A two-step reaction mechanism takes place with a tertiary haloalkane. 2-chloro-2-methyl propane reacts with sodium hydroxide in a substitution reaction to form 2-methyl-2-propanol. The 2 steps in this reaction are, so step 1, the bond between the carbon and the chlorine is broken. And so yeah, this would be broken. And we can see it's broken now with the chlorine is gone. And a new bond between the carbon and the OH is formed. And so here it is, the new bond is formed. Write the balanced overall equation using semi-structural formulas. States are not required. All right, easy. So, I don't like how they're written like this. I'm just going to write them in another easier structure. So what's happening? What's the actual reaction? It's 2-chloro-2-methyl propane. So let's draw that nicely. So it's propane, so it's 3 C's. And at the second carbon, it has a methyl. It's a chlorine and a methyl. So it'll look like this. Like that. Perfect. So writing its semi-structural formula, let's do that. So this, so C, it looks like a CH3. C, we have then a chlorine and another CH3, and then ends of the CH3. And yep, it looks like that. Beautiful. Plus, remember what we're doing is we're reacting that with sodium hydroxide, which is sodium hydroxide, and that results us in getting, so it's a substitution reaction. So when we're reacting NaOH, what's happening is this OH is substituting with that chlorine, and so this chlorine comes here. So now imagine this is the new form that this is the product. So this will be an OH and this will be a chlorine. So it'll be basically CH3C. Now this will be an OH. CH3. So yep, CH3 and then a CH3. Yep. Perfect. Plus, let me just move this to the left. There isn't a lot of space. Move it like that. Plus NaCl. NaCl. Beautiful. That looks good. No states are required, so that looks good. Identify whether this process is going to be exothermic or endothermic. Use item 10 on the data book to determine the theoretical enthalpy change associated with this reaction. Aha, so this is new in the study design. Normally the books don't tell you about this. I've looked at the Cambridge, I've looked at the Heinemann, I've looked at the Edrola. You would see that you wouldn't get an example of this. Now, I don't know why the books haven't put this, but I'm going to show you how to do this question. It is quite easy. So this is what is really happening. So I'm going to just take a picture of this. What we're going to need is this over here, this diagram, to really help us. I'm just going to copy. Okay, come down here. But really, why did I not? Oh my god, this is a pain. Why did it not let me? Yeah, screenshot. I'm gonna copy it. Yeah, I don't know why it's really. Okay, who cares? What I'm gonna do is I'm just gonna make my life easier. I'm gonna take this here. I want to duplicate it, make it a little smaller, of course. This is what I'm going to use to show you how to do this question. Make it a little smaller, put it right over here. Okay, so what's happening here? So identify this. So we need to understand, like, how do we calculate the periodical change in H? Now, think about it. Well, we know what's happening. So we know that, first of all, the bond, they've already told us the steps. The bond between the carbon and the chlorine are broken first. So this is breaking. Now, and you should realize straight away that isn't this over here. Remember, what is this? When it goes from here to here, this is the breaking of bonds. Remember, that step is the breaking of bonds. And that's why we need an activation energy. This is an endothermic process. You can see that we're needing some activation energy to, like, basically put it up to make sure, for the reaction to occur. So this is an endothermic, But then when remember this step here is where the bonds are formed. This is a formational bond, and this is an exothermic process, Now, this here is going to really help us to understand how our formula is going to form. How do we calculate the enthalpy change for like a periodical? And please make sure to write this down. This is, for example, the most of the books don't have this, so write this formula down because it can be used like in the exams. So what it is to calculate your periodical yield, your periodical change in H, it's gonna be your addition of your endo, so like the breaking, the energy of the bond breaking, so bond breaking. And you can see that, look, we're going to need energy to bond break, basically, minus the energy that is basically the formation of that bonds, the forming of bonds. Forming bonds. This is the actual formula. Please write this down. It is not in the data books and stuff. I don't know why. And most of the books don't actually teach this here. So please, this is used to calculate the enthalpy change when you have the bond energies. When you know what's breaking and what's forming. So let's look at what's breaking. What is actually breaking here? What are the bonds that are breaking? They've already told us that the chlorine, the carbon to chlorine bond is breaking. So if we're like, so this is breaking. So what is the energy that is used to break that bond? And we can calculate that looking at our data book. Going down, I think it's down here. What is so carbon to chlorine. So here it is, carbon to chlorine. This is how much energy would be used to break that bond. So that's what we're going to do. 324 minus the energy used to form the bonds. And what are the bonds forming? They've already told us. The step 2 is the new bond forming between the carbon and the OH, which is basically just the carbon and the oxygen. So carbon and oxygen, what's that? So we have carbon, oxygen's here. So 358. So put that 358 here. What's this going to give me then? Let's have a look. Easy, so 324 minus 358. That's going to give me negative 34 kilojoules per mole. Done. That is your enthalpy change, your physiological enthalpy change. Now, of course, like in this question, it's not really that, because you gotta think about it. When you're looking at the reaction itself, now they've made it easy for you, but yes, we know that this carbon to chlorine bond's breaking, but also you also had to add up that even the sodium and the OH bond will also break. But guess what? You don't need to worry about that because it's actually not in the data book. The sodium and the O, so you don't actually have to worry about that. So this is the actual theoretical, and you can see that it is negative. So it is an exothermic process. Exothermic. Is that it? Identify what process, so exothermic, and determine the theoretical yield. Done. I hope that makes sense. Please have this formula. I beg you to have this formula. It is going to help you. This formula here is a new formula to have. The rate of this reaction is controlled by the first step in this mechanism, the breaking of the carbon to halogen bond. So breaking of the carbon to halogen bond, so this bond. Okay. Explain whether the reaction between 2-iodo-2-methylpropane with sodium hydroxide would be predicted to react at a faster or a slower rate than 2-chloro-2-methylpropane under the exact same reaction conditions. Easy. Well, let's think about them. So 2-iodo-2-methylpropane, it's basically the same thing. It's just, so when we wrote carbon, 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 this was the chlorine and the methyl, look like this. And the other one, basically 2-iodo, it's the same, but what's the difference is the chlorine is iodo. But okay, remember they've told us the hint. The rate of the reaction, so how quickly the reaction goes, is determined by the first step, which is the breaking of the carbon and halogen bond. So this bond breaking. Now, which of these bond breakings will be occurring quicker? Easy. Because remember the bond breaking process, what do we know? It's this bond breaking process. It's the activation energy. So for the ones that actually have a lower energy, a lower energy that's needed to break that bond is going to occur faster, because what that means is, for example, if let's say the energy of one of them is lower, what does that mean? It means that the activation energy, you don't need a lot of energy to break the bond. So the activation energy is less. And hence remember, if the activation energy is less, it occurs quicker. So which of the following? So what is the, let's have a look at iodine and chlorine. What's the difference between those? So rubbing this. So, okay, carbon to chlorine is 324. Iodine, iodine is lower, much, much lower, meaning it has a lower activation energy and hence will occur quicker because it doesn't need a lot of energy to break that bond. It actually occurs quicker. So that is great for us. Yeah. So it's 3, let me just write the numbers. So 2, chlorine is 324. Iodine is 228. So I'm going to write a response. So we know straight away, if you react to iodo-2-methyl, it will occur at a quicker rate. Absolutely a quicker rate than the chlorine one, so the 2-chloro. So let's write a nice sample answer for this. So we're going to say is the bond energy of the carbon to iodine, which is 228 kilojoules per mole, is lower than the carbon to chlorine, which is 324 kilojoules per mole. And we know a weaker bond is easier to break. As it has a lower activation energy. Since the rate, they said that the rate determining step, so the rate is the breaking of the halogen and the carbon bond. Yeah. So since the rate determining step is dependent on the carbon, so carbon halogen bond, the carbon to iodine bond is weaker. So it's weaker than carbon to chlorine bond. Hence, the reaction of 2-methyl propane will occur faster than 2-methyl propane. I hope this goes into deep detail and helps you understand that. Yeah, it's not a bad, easy question. Not too bad. Perfect. That looks good. Let's have a try at 3 now. So, hydrogen chlorine fuel cells are being investigated for potential use for a grid-scale energy production. So the HCF fuel cell uses an aqueous acidic system. A diagram of it is shown. All right. Identify the energy transformations that takes place in the fuel cells. Easy. Remember, a fuel cell is just a galvanic cell. So, and remember, what is a galvanic cell? It transforms chemical energy, to electrical. Let me write that nice down. Done. Write the balance half equation for the reaction occurring at the cathode. Ooh. Alright, so if we know it's acting as a galvanic cell, what will hint us? Now, alright, wait. We actually got a little easy hint. Now, we don't have to go to our electrochemical series to determine that. There's actually a little hint they've given us. Look at the ions where they're moving. And look at these ions over here. These ions are going to help us determine which one's the positive and which one's the negative electrode. Think about it. So we know in galvanic cells, what happens is the positive ions go towards the positive electrode. Can you see how these hydrogens are moving to the left by these arrows? It means this here must be positive. It must be a positive electrode. These chlorine ions are going to the negative. They always go, remember, in galvanic cells, so the negative ions go to the negative electrode. So this must be negative, but it's vice versa. It's actually different when it's electrolytic cell. So the positive ions will go to the negative electrode, and so yeah, they're totally different. So, but in a galvanic cell, positive goes to positive, negative goes to negative. So that already tells me that this electrode is positive. And remember, if it is positive in a galvanic cell, it is basically the cathode, where reduction occurs. Reduction. On the left and on the right, it must be the anode, where oxidation occurs. Done. So the question is, write the balance half equation for the reaction occurring at the cathode. And remember, at the cathode, it's the left one, and it's just chlorine. So basically, where it's basically chlorine going for a reduction reaction and forming chlorine ions. And we can actually just determine that using our electrochemical series in this case. So remember, it is acting, it is going for a reduction. Let's go back to our electrochemical series. Where is that? Chlorine is right over here. Perfection, right over here. And done. You just rewrite that because you can see that the ion, remember, the electrons must be on the left because it's going for a reduction reaction. And it's perfect. You can see that chlorine gas reacts with these 2 electrons and forms these ions, these chlorine ions. That's what's forming here. So we can write that nicely down. Chlorine, 2 gaseous, plus 2 electrons goes to us, forms us 2 chlorine minus aqueous. Done. Beautiful. Let's go here. Okay. So place an arrow in the box shown on the diagram above to indicate the direction of the flow of the electrons in the Y. Easy. Now, because we know which one's positive and negative, so we need to just label it here. Remember, in a galvanic cell, electrons flow from the negative electrodes to the positive. So negative to the positive. So it's going to go like this. So it's actually in this case, it's going to be an upwards arrow. Done. Calculate the voltage that this cell would be expected to produce when operating under a standard conditions. Easy. Now we know it's just basic chlorine gas, which is a reduction reaction, reacting with hydrogen. So let's have a look at our electrochemical series. So chlorine, what's the voltage that's going to form? It is 1.36, that one. And what's hydrogen? Now, hydrogen is 0. It's the... Where is it? Oh my god, I can't even find it. There it is. Hydrogen. It's 0. So, you remember, it's the high... You always do this. Highest minus the lowest. And that's going to give you the voltage. So, it's basically just like 1.36 minus 0, which is just 1.36. So, the voltage is 1.36 in this case. 1.36 voltage, so V, volts. Done. State one design feature of the electrodes used in a fuel cell that would increase the efficiency of the cell. Now, you should start to realize, damn, what an easy question. One of the things about fuel cells is that the electrodes are porous, meaning that they basically have holes. Little holes. And what those holes do is they increase the surface area. And remember, if there's an increase in surface area, there's an increase in the rate of reaction. So basically, the gases are able to go inside of them, like inside the are able to diffuse much better and quickly. And hence, the rate of reaction is much better, quicker. So it's more efficient. So that is the first thing that comes to my mind. So state one design feature is just porous electrodes. You just have to state that. Porous electrodes. Of course, there's many more, but that's the kind of the easiest one in this case. Question F. A similar fuel cell is used in a school laboratory and operates for 3 hours at a constant current. The equation for the overall reaction in this fuel cell is this. Under SLC, a total of 300 milliliters of oxygen and 400 milliliters of hydrogen was pumped through the cell. Determine which chemical is the limiting reagent. Easy. Now you need to know in the study design, now you need to determine what is the limiting and the excess reagent. And you just need to make sure, this kind of used to be taught in the old study, not old study design, what am I saying? It used to be taught for the year 11s, like the year 11s you would have learned it in year 11, but they're now bringing it to the year 12 study design, so make sure you know that. And it's so easy, which one's the limiting and excess. How do you calculate it? This is what you do. So, you need to calculate the moles of both the reagents, so the oxygen gas and the hydrogen gas. So, what's the mole of oxygen gas in this case? Now, look at it. The oxygen, we've already given, it's at CLC, so we can use the formula N equals V over Vm, and Vm is always a constant, which is 24.8. This is in your formula sheet. So, if I need, for example, I know we have 350 milliliters of oxygen, so putting 300 milliliters in the volume, I get the mole of it. So, it would be 350 times 10 to the negative 3 because I want to make sure it's in liters. So like that. That's going to give me what? 4.8. That gives me 0.014. I'm just going to write 29, basically more. And what about doing the same for the hydrogen gas? So make sure this is about, and for the hydrogen gas, it's just 450. This is just a 4 here. Okay, so 4 here, we get 0.018145, basically approximately 2 mole. Now, this is how you determine which one's the limiting excess. The limiting is always used up. The excess is like left over. It will be left over. Some of it will be left over. How do we determine it? This is what you do. Very easily. You choose one of them. You choose randomly one of these to use for your for your calculations. Now, in this case, I'm just going to use this oxygen. You can use any of them. You can use the hydrogen or oxygen. But I'm going to use the oxygen. You just choose one of them. Now, using this oxygen as my mole, like the mole of oxygen for my calculation, I'm going to try to calculate the mole. What would be like the mole that's used up for the hydrogen? So using the mole of oxygen, the one that we're using, what would be the mole of hydrogen gas that would be used up? And it's easy to calculate. It's a 2-to-1 ratio. So the mole of hydrogen gas using the oxygen gas, because it's a 2-to-1 ratio, it's 2 times the mole of oxygen gas. So that gives me, what's that? 0.0141129, and you times it by 2. You basically get this. You basically get 0.0282 mole. Now look at the difference. So when we use oxygen gas and we try to calculate the hydrogen gas, how much we'll be using, we'll be using this much. Now look at the difference. This is the true one. So what's the difference between them? This one over here is so much higher than this, meaning that when we used oxygen gas, we got a higher value for the hydrogen gas, meaning that this oxygen gas gives us excess. This one here gives us excess amount in our calculation. It means that hydrogen must be our limiting. Again, let me explain it again. So we use oxygen gas for our calculation and we try to calculate how much hydrogen gas was produced. We got this. Now this here is higher than the overall normal hydrogen, meaning that when you're using oxygen gas for your calculation, it's going to always give you the excess amount. It's going to give you more than what's used up. So this has to be excess and the other one has to be our limiting. Done. So, I mean, rub this. It's only 1 mark. You don't need all these calculations. But so we know already our limiting is our hydrogen gas. Is hydrogen is limiting. Limiting reagent. That's it. Done. Calculate the volume in liters of the unreacted gas. Easy. Remember how we said oxygen gas, because it's in excess, only some of it's going to be used. There will be some left over, and that's the unreacted gas. Let's calculate that. So, by the way, when you're doing calculation, we're always going to use our limiting for calculation. The real, like that true one, when you do calculate, you always use your limiting because it's always going to be used up. It's always going to use up. You never use the excess. So, let's think about it. Oh no, why did I even take everything off? This was stupid of me. So let me go back. I'm going to use this. I'm going to need this here. I'm going to be needing these two here. These are going to be really helpful. So I'm going to just bring this here for our calculations here. Let me take this out. And let's just say, again, hydrogen gas was our limiting reagent. Limiting reagent. Beautiful. So we want to basically do this. So we've got oxygen gas and hydrogen gas. Because remember, this is our limiting, so we're going to be using this for calculations. Remember, this is excess right here. This is the excess. That's how much we have. We have this much, but it's in excess. So we're going to be using this for calculation, and we're going to actually calculate how much oxygen gas would be used up. Because remember, this here, we're going to use this to calculate how much oxygen gas would be like used up. So let's do that. The amount of oxygen gas that will be used up using our hydrogen is what? So it's a half ratio. Like if you're using hydrogen gas and you're going to form oxygen gas, it's a 1/2 ratio. So it's basically half times your mole of hydrogen gas, so 0.0181452. That's going to give me what? 0.0181452 times 0.5. You get 0.0090726 moles that will be used. So think about it. This is how much we have initially. Like this is how much we have, but we're only going to be using this much of the oxygen. So what's left over? The leftover, so the oxygen that's, I'm going to write L, leftover, is the initial, which is that 0.0141129 mole, minus the one that we're going to be using up. 0726. That gives me what? So 0.014112.9. Did I write it right? Minus that. We get 0.0050403 mole. Now we've got actual mole that is going to be unreacted. Now we can just calculate the volume using our N equals V over Vm, which is 24.8. So basically multiply this mole by 24.8 and we get our volume. So the volume of oxygen that's going to be unreacted is 24.8 times that 0.00504 blah blah blah. And that's going to give you 24.8. Overall, I get to how many significant figures? Everything looks like it's 3, so I'm going to write 3. So 0.125 liters. Done. That's your answer. Not too bad for a 2-marker. All right. Question 4. Let's have a try at this. A biodiesel consists as a pure sample of fatty acid methyl ester. The molecular formula of this compound is this, and its molar mass is this. All right, so it's a fatty acid methyl. It's basically biodiesel. A fatty acid methyl ester is a biodiesel molecule. Calculate the mass in grams of iodine that would react with 100 grams of this biodiesel. All right, easy. So we need to think. So, like, remember, when you're reacting like iodine, this is going to go for an addition reaction. So iodine will only react if this compound has double bonds. If it has no double bonds, it's not going to react. If it does have a double bond, then it does react, because it will go for an addition reaction. So now you need to kind of determine how many double bonds there are in this molecule. The way you do it, I think the most easiest is actually drawing it, like to have a like estimated, not like to draw how like a methyl ester would look like if it was saturated. So for example, imagine, we know it starts off like these. They start off like this, and they basically like a very long, starts off like a long, and then at the end it has a ester group and a methyl ester here, and methyl group here. This is what the actual arrangement looks like. Now, that's what's like basically every fatty acid methyl ester has. This this part, and this part always. And they always in the middle have all these like basically every carbon has 2 hydrogens, and it goes for if it's saturated, meaning that it has no double bonds. So now what I'm going to do here is I'm going to check if this makes sense in this equation here. So I know that I'm going to minus these from it. So there's 3 carbons, so it'll be C16, and we'll also have minus 3 hydrogens, so 3 and 3 here. So that'll be 36, so it'll be 30. And oxygens will also minus them. So basically, what would be this here would be the amount that will be left in the middle. Now, if you remember what we said, if it was saturated, every carbon has 2 hydrogens. Now look at this. So every carbon, so if I double this carbon amount, it gives me 32. This here, it should give me 32 hydrogens if it was saturated. But the problem is it gives me 30. What does that tell me? It tells us that there's only 1 carbon-to-carbon double bond. Because remember, if you have 1 carbon-to-carbon double bond, 2 hydrogens are taken out. So imagine here, that 32, if you take 2 out, it's 30. And that's what it looks like it is. So there's only, in this whole molecule, there's only 1 carbon-to-carbon double bond. Easy. So only 1 carbon-to-carbon double bond. So now, and remember, every 1 carbon-to-carbon double bond, when it goes through a addition reaction, so when you every like 1 carbon-to-carbon, you react with 1 like 2 iodines. So what happens is this carbon-to-carbon double bond will break. It will go through an addition reaction, and it will form 2 iodines here. So it'll look normal then. So absolutely, that's what it will look like. Done. So that in this whole thing, there's only 1 1 carbon-to-carbon double bond. So it will look like this. When we're reacting C19, let me write the reaction. C19, H36, oxygen gas, with 1 iodine. Remember, because this has 1 double bond, so you're only going to react with 1 molecule of this. It will give us, remember, an addition reaction is basically you only get 1 form of product. So it's going to give us C19, H36, O2. I'm writing in its molecular form, I2. Done. That's what it's going to... Now, you should just realize that everything here is a 1-to-1 ratio. So this is going to make our calculation so much easier. So we need to calculate the mole of... To calculate the grams of how much iodine would be reacting, we need to first calculate the mole of biodiesel. So it's C19, H36, oxygen gas. Is what? It's basically mass over molar mass. And they give us the molar mass to be 296. And that's going to give me what? 100 divided by 296. 0.337837 mole. Done. Now, because it's a 1-to-1 ratio, the mole of the biodiesel, CCH3, 6 oxygen gas, is going to be equal to the mole of iodine used. Done. So the mole of iodine is basically the same as this. In other words, 0.337,837 mole. Done. Now we just need to calculate the mass now. So remember the mass of iodine, how do you calculate it? You multiply by the mole by its molar mass. So the molar mass of 2 iodine molecules are what? Atoms are... So if you go iodine into a... Iodine... Not here. Iodine is here, right over here. It's 126.9. 126.9. Done. Let's put that back. And that's going to give me times 2 times 126.9. It results me in how many significance? 3. Everything looks 3. It basically results in a mass of 85.7 grams. Done. 85.7. Easy. That's what it will be. Not a bad question. I mean, it's not too bad. B. Using the molecular formulas. So we're going to use molecular formulas, write the chemical equation for the reversible transesterification reaction that produces this biodiesel. Assume that 3 identical fatty acids form this triglyceride. Easy. Now you should straight away realize, the transesterification reaction is basically when you take a triglyceride, and you react it with 3 methanol molecules. Oh my god, methanol molecules, and because it's saying it's a reversible reaction, normally you react with KOH. This is the catalyst that's used to do this transesterification reaction, and we basically form 3 biomedicinal molecules. So the 3 methyl esters. So 3 fatty acid methyl esters. Say fatty acid methyl esters. In other words, they are just biodiesel. And then you get out a glycerol molecule. Make sure you remember this. This is one of the easiest. You need to memorize this reaction thing. How the transesterification reaction. So knowing this here, and remember, what makes this actually easy is because they're telling us that there's 3 identical fatty acid methyl esters. This is going to help us because writing this reaction, let's write it down here. So put these here. Oops. So we already know we're going to have 3 fatty acid methyl esters. So 3. What's our fatty acid methyl esters, which is our biomedicinal molecules? It's these ones over here. So it's going to be C19, H36, oxygen gas, oxygen. Yep, that is it. So 3. I don't think you need to write what do we say? The states, because what the hell? Yeah, I think you wouldn't want to write them in this case. There's too much. So yep, you have those plus glycerol. Now glycerol is actually in your formula sheet, the molecules. So we just want the actual, what do you call it? The molecular formula for it. So I think going down. There it is, right over here. Glycerol is how many carbons does it have? It's 3 carbons, so C3. How many hydrogens? You have 1, 2, 3, 4, 5, 6, 7, 8. We have 8. And how many oxygens? We have 3. Done. So we already got the right-hand side. Now, 3 methanols. So 3 methanols are remember, methanol looks like this. So OH here. Looks like that. So it's a C. 4 hydrogens and 1 oxygen. Looks like that. And there's 3 of them. So 3 we said. Alright, so that. Put it right there. And then our triglyceride. Now, it's easy to get the triglyceride because we've already got everything. Like, how many carbons on the left, on the right must be the same carbons on the right. So 3, how many carbons on the right? So we have, so on the right we had, so 19 times 3 plus 3. We have actually 60 carbons. So carbons, we have 60 carbons here. Here we already have 3, so the leftover ones has to be 57. Easy. What about the hydrogens? Well, remember how many hydrogens on the right side? So right side, so 36 times 3 plus 8 there is 116 hydrogens on the right. How many here? We have 4. We have 12. We only have 12 here. So how much is left over? That's minus 12. 104. So this here is 104. Now oxygens. Let me just a little bit move this to the left. How many oxygens? So on the right side we have 6 plus 3. So there's 9. And so there must be 6 here, because there's already 3 oxygens here. Done. There's a lot. Oh my god, it's a lot of things to write. I'm just gonna rub it and make it nicer now, because it's just too much for that little space. All these kind of work. It's actually, yeah, it's not a good question, I would say. Just it's a mess. It's a mess of a question, but that is your reaction. So it's reversible. Now, I wouldn't say you would want to write that KOH. That's normally, you remember that's, yeah. So you normally use the catalyst of KOH here. The concern is that I'm having is, because it's a reversible reaction, normally we put that KOH to make sure, I think, to make it go on only like in the direction one, the forwards direction, we use that catalyst. But if we have, yeah, if we have that, yeah, I don't think there's no worries. I'll put that KOH myself there. Don't worry about it. Just put that there. There it is, KOH, done. So it should look like something like this. Easy. Took actually quite long for this one. Transesterification is a reversible reaction. Explain one way the yield of biodiesel could be maximized. Easy, just use the Chantley's principle here. So, one of the easiest way is to kind of just look at, like, you can say the glycerol molecule or the methanol. So think about it. If I decrease the methanol, like if I decrease the methanol, what would happen? No, you don't want to decrease, actually. You want to increase it. So if you increase methanol by the Chantley's principle, what's going to happen is the system is going to be like, wait, there's too much on the left-hand side. There's too much methanol. I need to find a way to get rid of it. So it's going to go for the forwards reaction to get rid of that methanol. And so if it goes to the forwards, so we're going to form more of that biodiesel. So perfect. So basically, one way is, there's many ways, but I'm just going to think of the basic ways. There's one way you can say it's just basically increasing more methanol, like adding more methanol. And also, what about, you can also decrease that glycerol. So as you know, when you're forming that glycerol, take that glycerol out. If you're removing that glycerol, the system's going to be like, wait, there's not someone's taking that glycerol. I need to find a way to make more. So it's going to try to go more for the forwards reaction. So these are 2 possible ways you can get the answer. You only add one, but I'm going to write both of these just so if students get these, you can write. If you get any of these, you get the answers right. Of course, there's more, but these are the most basic. I'm going to write the most basic in this case. Actually, I'm just going to write one, but yeah, if you have any of these, yeah. So, actually, I'll write both of them. I don't want to confuse most of the students. So first one is add methanol. So if you add methanol, and you need to explain it, so for every, so it's just one way, and you need to explain it, because it's a 2-mark question. So increasing concentration, so concentration of methanol shifts the equilibrium, so shift the equilibrium, shifts the equilibrium of the reaction, towards the formation of more biodiesel, and glycerol, according to the Chantley's principle, I think that's how you spell it, principle. Still can't spell it. Who cares about spelling it? Just the principle is there. So you can add methanol. That is one of the possible ways you can do it. Or another possible way is, like we said, you can remove that glycerol. As you know how the glycerol is going to be forming, just remove it constantly. Or you can basically, again, remove glycerol. So if we remove the glycerol, the reaction further drives the equilibrium to the right, to the right. Increasing the yield. Increasing the yield of biodiesel. According to by Le Chatelier's principle. So any of these, and just saying about something with Le Chatelier's principle, you get the mark. That's how I would think you would get the mark for those. Easy. That's nice questions. That's another one you can state. Like these two are the possibilities. There's more, but these are the most basic ones you can get. All right, D, let's have a look at this one. Okay, it says the energy content of biodiesel was investigated by two students, Birani and Jack, using the equipment shown below. They ignited the biodiesel under a beaker containing 200 grams of water, which was set on a tripod. Beautiful. Looks good. A sample of 0.51 grams of biodiesel was burnt. Birani recorded that the initial temperature of the water was 225 degrees Celsius and the final temperature is 35.7 degrees Celsius. Assume that the biodiesel is fully combusted and that the system was known to operate with a 55% energy transfer efficiency. Calculate the energy released by the biodiesel in kilojoules per gram based on the experimental result. Not a bad question. It's one of the most common kind of questions that come out with exams. And let's do it. Well, the first thing is I know the mass of the water. Yeah, remember how, so if you're burning biodiesel, most of the energy would have gone to the water. Of course, in terms of that 55%, so only 55% of the energy of that, when you burnt that biodiesel, would have gone to the water. And so we just need to calculate how much of that energy went to the water. And that's easy because using E equals MC delta T, we know the mass of the water is what? It's 200 times the 4.18, which is the specific heat capacity of water, times the temperature change of the water, which is 35.7 minus 22.2. That will result me in what? Times 4.18 times 35.7 minus 22.2. That gives me, I'm going to divide by 1,000 to make sure it's in kilojoules. I think that'll be very easy. So 11.286 kilojoules. That's how much energy was given to the water. But of course, you got to remember that not all, so when you burnt that biodiesel, not all of it went, some of it went to waste, of course, but only this amount went to the water. But we need to get the original how much the biodiesel when you burnt it was giving out. And so to do that, well, think about it. You would this is what you would do. So the original biodiesel energy, you would multiply it by 0.55%, yeah, to get that energy that was given to the water. So, but if we want the original energy, we just need to divide both sides by 0.5. So basically meaning that to get the original energy, this here, the water that was given to the energy that was given to water, you just divide it by 0.55, and that will give you the original that was burnt, that the biodiesel gave out. And that gave basically the energy that basically biodiesel gave out was 20.52 kilojoules. Done. Now we just need to get in kilojoules per gram, so that's easy. Just divide. So this is kilojoules. You just need to divide it by the mass to get in grams. So how much did we burn? We burnt 0.510, and so that's going to give me the kilojoules per gram, 0.510. And so the energy overall, the energy released, how many significant figures in this case? I think it's all 3. Yep, looks 3. So 4.2 kilojoules per gram. Done. Easy. That looks good. For free marker, that's nice. That's just a normal common question that you get from like the VCA questions. So this is nice for a free marker. Question E. The following 3 molecular formulas represent members of the same homologous series of fatty acid methyl esters. So basically they all have that biomedicine look. So all of these. Explain how the viscosity of these compounds will vary. Okay, so basically they all have the, like if you're drawing them, again, they all look the same. So they'll look like what we've drawn. They'll all have this, and they'll at the end have this fatty acid methyl ester group. Now, what determines, remember, viscosity is like the rate of resistance. Basically, like the difference to think of it is high viscosity is like honey. When you take honey and you pour it down, it takes so long to come out of the bottle. But if you take water and you pull it out, it quickly goes up. So because its viscosity is less. So high viscosity, think of it as like honey. So, and it's all about if you have so for it to be high viscosity, it's all about its intermolecular forces. If it has high intermolecular forces, then it will have a high viscosity. Now, because all these molecules are the same methyl, ester, they all have the same this part over here. This part here is basically where the dipole form will. Now, you don't need to worry about that because all of them have that. All of them actually have that. So the only force that is most important is the dispersion forces. The dispersion force is what's going to really tells us the difference between those viscosities. Yeah, but before we even do that, we need to be careful. This is where they kind of trick you. If there are double bonds in these molecules, the viscosity destroys itself. It's like it decreases by a high amount. And this is because there are kinks. If there are kinks, let me explain. So if you have, let's say, enough of a nice fatty acid methyl ester, but then when there's a kink, a double bond, can you see how it's not able to be, basically, it won't be able to branch? And so its viscosity decreases. The intermolecular forces actually are not that strong. So if there are kinks, the viscosity destroys. We need to be careful with this. We need to check if they all like have any, if they all have, any of them have double bonds. So let's do that. Let's look at the first one. Same thing. Remember following the structure to determine the double bonds? It was quite easy. Remember? This here, they all have this. So let's minus that out. So we see minus how many carbons? 3 carbons. So it'll be C16, H. Remember, you minus 3, so it'll be 30, so minus 6, and oxygens will take them out. So the overall, if it was saturated, if it didn't have any double bonds, it will always every carbon will have 2 hydrogens. So this carbon, if it had 200, it will be 16 times 2, which is 32. But it's 30, so it means that it has 1 double bond, because if there was 1 double bond, 2 hydrogens will be taken out, and so this will be 30. So this one here only has 1 carbon-to-carbon double bond, and we'll check that with the other ones too. It's just the same thing, remember, just the same pattern. Let's do this here. So remember 17, so what we're going to do is, what are we doing? Again, so minus 3, you're going to minus 3 carbons. So 17 minus 3, which is 14. Hydrogens, remember, you minus 6. So it'll be 26. Yes. And oxygens, okay. So doubled the carbons, it's 28. Aha! Also, this one's minus 2 of them. So this only has 1 carbon-to-carbon double bond, like the other one. Let's do the same with this one. So minus 3 first. So that'll be 12. Then you minus 6 from this, it'll be 22. Okay, and so 12 times 2 is 24, and then, but there's 2 out here, so it means this also had a 1 carbon-to-carbon double bond. Done! All of them have 1 carbon-to-carbon bond. Doesn't matter. This means that all of them have the same kink, so we don't have to worry about like one having having a higher double bond. So all of them have, so that it doesn't matter. The double bonds doesn't matter. So it's all about the dispersion forces, how long the chain is. And that's easy. We can see that, of course, the first one is going to have, it's a very longer chain, so it has more stronger dispersion forces, hence its viscosity is increased. It's the highest. This one's going to be the second, this is going to be the third. Done. So just make sure, check if there are kinks. Kinks are dangerous. This is where they can trick you. So done. So luckily this one's nice and easy. It's just because all of them had all 1 carbon-to-carbon double bond. So we're just going to write as the carbon chain length of fatty acid methyl, so esters, increases, viscosity also increases, due to stronger intermolecular forces of the dispersion forces. Remember, there's only dispersion that's going to really define them. Dispersion forces. Therefore, so we say therefore, so C19H36O2 will have the highest viscosity. So will have the highest viscosity, viscosity, while the C15 one, so the H28, will have the lowest. So will have the lowest. Done. Beautiful. 2 marker, that's nice. Question 5. This is the last question, and I think this here looks like it's some, medicinal chemistry. Not too bad. Let's have a smash at this. So it says inflammation is a physiological response that causes swelling to occur around an injury. Ibuprofen is, I don't even know how to say it. Ibuprofen is a common anti-inflammatory drug. So it can exist. So anti-inflammatory drug means like, so if it was inflammatory drug, it makes inflammation. Anti means it stops inflammation. So anti-inflammation drug, it can exist in 2 slightly different forms shown below. Only the S-ibuprofen form is biologically active. So we got 2 forms. So remember, these are optical isomers. One is R and one's S. So basically they're not the same molecule. Be careful, not the same. They are like the actual same, but they are mirror images of each other. So here it is. You can see these are the different parts. In terms of 3-dimensional structure, they are actually different because these 2 are going to be in different. One's going to be like, I think, so this one's going to be like back, like it's going to be behind. This one's going to be in front. And yeah. So this is what really defines them. It's the R and S. So R means that this basically rotates, like the high polarity rotates it clockwise. This one's anti-clockwise. You don't need to know that, but yeah, totally. Consider them as totally different compounds. Do not consider them the same. They're just optical isomers. So when your body feels pain, it responds by producing prostaglandins that then cause inflammation around a pain area. So around the pain center. Ibuprofen is a weak competitive enzyme inhibitor. It inhibits the enzymes that form prostaglandins, which limits inflammation. That's good. Ibuprofen has little impact on the body. This is what I was talking about. Look, so ibuprofen is very useful. It stops inflammation. This one over here, it's useless. Totally different chemical. I know they have the structural similarity. Absolutely perfected. Like they are same. Like I would say, you don't want to say it's the same structure. They are kind of different, but you would say like everything's the same about them. Every physical thing is the same. Properties. The physical properties are all the same, but they totally have different chemical properties, like what we just saw here. The S-ibuprofen is useful. The R-ibuprofen is quite useless in the impact on the body. Discuss whether the melting points of these 2 forms of ibuprofen will be the same or different. Easy. So, remember, melting point all depends on the intermolecular forces. If you look at these 2, they have similar structures. They're like everything's similar about them. Of course, they're different. Only this is different. So that's not going to do any difference. But remember, it's all about, they have similar structures. And so the intermolecular forces are going to be the same. Hence, the melting points are going to be the same. So all you need to know is this. On optical isomers, the physical properties are going to be identical. But the chemical properties are going to be totally different. It's because chemical is more, it's more sensitive to differences like these here. But in terms of physical properties, they are the same. So like if it talked about boiling point, melting point, or densities, they're all the same for both of these optical isomers. So yeah, they will have the same melting point. Easy. Let me write it with this color here. So we're going to say the intermolecular. I'm going to write a lot just to show students, let students understand. So the intermolecular forces determines the melting point. The melting point of substances. Beautiful. Because both forms of ibuprofen have similar structure. You don't want to say the same structure. Be careful because they actually don't have. One is you can see one's into and one's out the page. So have similar structure. So have similar structure. They will have similar intermolecular forces resulting in the same melting point. Now this is just an extra I'm going to write. This is important. As optical isomers, the two forms have identical physical properties like density or melting point or building points, despite they will have, as optical isomers, the two forms have identical physical and different, so we're just going to, and different melting points and different chemical properties. Done. That's it. So remember, optical isomers have, of course, identical physical properties, but chemical, in terms of chemical, absolutely not. Totally different. And that's, it's very easy to marks there. B, explain by referring to the substrate-enzyme interactions. What is meant by the description of S-ibuprofen as a competitive inhibitor of an enzyme? You may use a diagram in your answer. Easy. This is new in a study design. So a competitive inhibitor, what is it? Well, let's draw a nice diagram to represent this. Say we have an enzyme. Say we have this enzyme here. Okay, here we have this enzyme. And say we have this nice, what we call, let's say we have this substrate. And this substrate is what causes, it produces prostaglandins, those things that, create inflammation. So this one produces, let me just kind of, let me put it here. So like imagine that. So this is the, make it a little bit here. Straight, and this is the one that produces those, basically produces inflammation. I'm going to say inflammation. It's those prostaglandins. I don't even know how to say it. So, this is the, what happens basically is you can see that this substrate perfectly fits, I mean, it's not the most nice, but it perfectly fits the enzyme active site. But what S-ibuprofen, what it means by it's a competitive inhibitor is basically it has approximately the same basically it has this like the same similar structure as a substrate. So this S-ibuprofen, what do we mean by competitive inhibitor? This is what we mean by competitive inhibitor. Basically, S-ibuprofen, it competes with this substrate, the one that produces this inflammation. They fight each other. But because S-ibuprofen is much stronger, it's able to take the position of that substrate and hence fit in the enzyme. And now, guess what? This substrate, the one that produces those inflammation, is not able to fit in there. It doesn't have anywhere to go. And so that is why S-ibuprofen is what we call a competitive inhibitor. It stops the substrate from producing those prostaglandins and hence inflammation. I hope that makes sense. That's what a competitive inhibitor is. It competes with that substrate for the active site of the enzyme. And so it blocks that substrate basically from binding and hence creating those prostaglandins. And so this is a nice structure. We're going to basically put this right over here right now. I'm going to put that right there. I'm going to write my, what we just said. I'm going to be like very, try to be detailed so just to make students understand. Let's use this over here. Let's use green. Okay. S-ibuprofen compete with the substrate for binding to the active site So active site of the enzyme. Done. This means that the S-ibuprofen, I don't know, I hate writing it, but ibuprofen has a similar structure to the substrate that creates prostaglandins, I think, glandines, it sounds like that. Yep, prostaglandins. When S-ibuprofen occupies, so it takes that place, occupies the active site, so yep, so when it occupies the active site, it blocks the actual substrate from binding. Done. Hence preventing inflammation. Perfect. So this is a nice diagram that really explains what happens. So I'm going to write, there's no place for it to be honest, but I'm going to put it right over here. I hope that helps with that question. Nice, it's actually not too bad. So this is in the new study design, so make sure you know what competitive inhibitor is and non-competitive inhibitor. But this is what competitive inhibitor basically means. It competes with that substrate for the active site. Next one, state one reason why our ibuprofen is not effective as an anti-inflammatory medicine. Like what we said, why? You remember how we said that the chemical properties are different? This is because why? Because you remember ibuprofen, yes, it has all the similar structures, but because it's an optical isomer, its three-dimensional structure is totally different. What do we mean by that? Well, let's think of it like this. If I draw a diagram, I think a diagram would make more sense. So think about it. This is the S-ibuprofen. Let's say this is your S1. So let's say this is your enzyme. This here is your enzyme, and it basically, remember enzyme, it's so specific. It's so specific. Let's say this is what it needs. It needs this. I mean, this is not nicely drawn, so let me actually draw it nicer. Like this. Imagine this is your active site of your... this is your active site of your enzyme, and basically has, let's say, these... this is the active sites that it needs. So like a triangle... a circle, and so this here is your let's say this is your S-ibuprofen, so it fits perfectly. So like you can see, everything is complementary, like everything fits nicely into it. You can see that this over here, beautiful. When you feel like, if you put it, it's like a puzzle piece. You put it, it fits perfectly. But because this is S-ibuprofen, but because it's an optical isomer, remember optical isomer it's a mirror image. So basically now this part here looks like this. This is what our ibuprofen looks like. This is the circle. So that's that part here, and that's the circle. So look, that's the mirror image. And so imagine the same active site of the enzyme. Oh, I hate this. Why does it look? Yep, like that. Look, imagine that's the same. I'm going to duplicate this. Put it right over here. The same active site. Does it fit anymore? Like, does it fit? No, it doesn't. You can see that the circle doesn't fit here anymore. The triangle doesn't fit. And as many times you want to rotate it, it won't fit. It won't be complementary. They will never fit perfectly. So this is why it's so important to have the perfect, everything needs to be perfect. So that's why S-ibuprofen is able to fit into the enzyme and hence stop, inflammation. Whereas S-ibuprofen, it doesn't even fit. So yeah, it's useless in that case. So this is what we just need to basically understand. It's a one marker, but I hope this makes sense. Because it's an optical isomer, its three-dimensional structure is totally different. Yeah? Meaning that its spatial arrangement, these spatial arrangements of these here are different, and hence prevents the ibuprofen from fitting into the enzyme's active site. And hence, it's not stopping the production of prostaglandins, those things that form the inflammation. I hope that makes sense. So this here is just a nice little thing for you to use to help you understand with that one. So let's write what we want to write. I'm going to write what I just said. Try to be as detailed as I can. So for students, let's try here. So ibuprofen is not effective as an anti-inflammatory medicine because it is an optical isomer. So optical isomer of S-ibuprofen. Meaning it is a mirror image. It is a mirror. It's a mirror image with different three-dimensional, I want to say 3D, but I think that's not very dimensional structure. I'm going to write it in more nicely. This different spatial arrangement prevents it from fitting properly into the enzyme's active site. So into the enzyme's active site, hence cannot inhibit inflammation. Hence cannot inhibit the enzyme producing inflammation, producing blah blah blah, inflammation here. I'm just gonna write it here. Inflammation. Done. There it is. Yeah, hope that makes sense. The last one, let's smash this one. The structure of naproxen and morphine are shown below. Like ibuprofen, these drugs can be used for pain relief. So, okay, state which molecule, naproxen or morphine, would be most likely to work through a very similar pathway to S-ibuprofen. Give the reasons for your choice. So, like we said, if it, works in the same similar structure, it means it fits it probably has a lot of similarities. Let's look at the difference. Now, I'm not joking. Naproxen looks the most closest to these. Yeah. Wait. They have the same methyl, the alcohol, the carboxylic acid here. This one has nothing. It also had that CH part here too. Look at that CH here. That CH. And also has the ring. The benzene ring. Yep. See, yes too. Look. That and the benzene ring. Well, the other ones are not, and then totally different. This is great because if it has a part of it that is similar to the S-ibuprofen, it's able to work a similar pathway. Whereas this one over here, it has alcohols. The other one didn't even have alcohols, and it has a lot of these mixed up rings. So it looks like naproxen would be the best because think of it you would if you have an enzyme. I mean, it probably won't fit, but it's not a best analogy. But because naproxen has quite a similar structure, this part would actually a little bit fit into the enzyme and has probably going that similar pathway. Yeah. Whereas compared to morphine, which is totally a garbage molecule. No, don't think that morphine doesn't it doesn't cause pain relief. It does, but it will go through another pathway, not the similar pathway as what we're going to go through ibuprofen. Yeah. Not a bad question. Wow, naproxen. So naproxen, I would say, would be the best in this case. And that's because, what was it? It had the same carboxylic acid and the benzene, I would say. This one, yeah, also that one. But I'm going to say naproxen, like S-ibuprofen, ibuprofen has a similar structure, that includes, the basically COOH, the basically carboxyl, and benzene ring, This structural similarity, suggests that naproxen can interact with the same types of targets as ibuprofen. Now I think we'll just do an extra here, and we're going to talk about why morphine doesn't fit. So we're going to just say, in contrast, morphine has more complex ring structures. Let's say complex ring structures and functional groups. It has more like those alcohol. So functional groups. Of course, you don't have to write this whole thing, but I just want to make sure when you read it, you can fully understand what I mean from my answer. That are quite different. From those of ibuprofen, and naproxen, indicating a different pathway. Done. Easy. This paper was actually not bad. Like this overall, yeah, this is like the half of the exam, but not an actual bad exam. I did write a lot to try to go as detailed as I can to help you as much for the students, especially it's a new slide design. There isn't a lot of it is quite complex, you would say. Yeah, but not as bad as I thought. It looks quite nice. Please let me know if I make any mistakes. Sometimes I do a lot time, so please let me know. But yeah, it looks not too bad. I'll hopefully go for the next part in the next video. Thank you guys for watching this video. Please make sure to like and subscribe for more future videos like this, and I hope this video finds you well, and please take care of yourself, guys. Bye bye.